and providing some of the theory around forecast reconciliation. And that's the topic he's going to talk about today. So please join me in welcoming Anastasios Panagiotelis.
Okay, thank you for that kind introduction, Rob. And also, I'd just like to exploit my position as the last keynote to say a few words about the conference. So Laurent referenced in his opening remarks how great it was to be bringing this conference to mainland China for the first time, referencing China's large population, large and dynamic economy. But I think over the past few days, we've been treated to an exhibition of Chinese soft power. The contributions of the scholars to our international research community, the amazing cultural event last night, and of course the hospitality of the local organisers. So I'd just like to personally thank the local organisers, led by Yang Miao, Jue, Yanfei, Feng, Xiaochen, and the small army of student volunteers. Okay, so let's get started on this talk. I felt I had to give it a suitably pompous sounding title since it is a keynote, Geometry, Optimisation and Beyond. But this is a talk really about the last few years of forecast reconciliation and hierarchical time series. There's been many talks on this throughout the conference already, and many of you in this room are familiar with what this field is about, but not all of you. So I will give a brief historical background in the first section. In the second section, I will talk about how we extended that to probabilistic forecast reconciliation and the importance of the geometric point of view in doing that. The next three parts are three little snippets, three more recent pieces of work, all in various stages of incompleteness. One about quantiles, one about nonlinear reconciliation, and the fifth one there is about how we can use hierarchical forecasting methods even when we're not working with hierarchical data. And then finally, I'll wrap up with a few comments. Okay, so let's get to the beginning. What are these hierarchical time series that we have multiple sessions about at IIF over the last few years, ISF over the last few years? Well, at its most general, we're talking about multivariate data, so multiple time series. We need to forecast more than one time series. And these time series are bound together by some constraints. Typically, these constraints are linear, although later I will present some new work on nonlinear constraints. And why do these linear constraints arise? Well, most commonly they arise due to an aggregation structure. In other words, some of our time series are aggregates of the other time series. And we're interested in all of these time series, both the aggregated series and the disaggregated series. But this is where the name hierarchical comes from. Although they need not be hierarchical, time series with any constraints fit into this framework. Now, we do have a lot of different structures for this aggregation. There are grouped or cross aggregation. We also have temporal aggregation. So that's where we look at just a single time series, but take aggregates over different frequencies. There's also the mix of those two, cross-temporal. I won't cover that work today. There's quite exotic types of aggregation that happen. But today I'm just going to stick to simple examples. So this is an example of a hierarchy. At the top, we have the total sales. It may be sales of bottles of water. And then suppose now for this particular company, they operate in two regions, region 1 and region 2. So the first way we can disaggregate the total is into our two regions. And then maybe the regions each have two stores. So the time series for store 1A and store 1B will aggregate to the time series for the first region. Likewise for store 2A and 2B. And of course, both regions aggregate to total sales. Now, one way of representing the schematic that we saw on the previous slide is through some matrix algebra. So I'm getting it out there early, but this is the typical way that this type of a hierarchy was characterized in the earlier literature. And what did we do there? Well, we would have on the right-hand side some bottom level series denoted by the vector B. So those are our store level time series. And on the left-hand side, we have all of our time series, both the bottom level and the aggregates. And then we have this S matrix, a structure matrix, which basically gives us the full vector from the bottom level series. So across the top row there, you've got all ones because you simply aggregate the 4 bottom level series to get the top level series. And likewise for the regions. So keep this S matrix in mind because it will pop up again. Okay, so we know that our observations, at least in the context that we're working, we have observations that always cohere to these constraints. The linear constraints will hold for the data that we actually observe and for the data that we're going to try and forecast. However, the forecasts may not respect these constraints. Now, why might that happen? Well, for a start, different forecasts may be made by different agents. So going back to our previous example, there may be one team making the forecasts and a set of decisions around those forecasts at the aggregate level, and there may be different teams making forecasts at the bottom level. And when you put all of these forecasts together, it may be the case that the bottom level forecasts don't add up to the top level forecasts. Okay? Now, you might say to yourself, well, why not just come up with a model that guarantees coherence from the beginning? And that's actually a lot trickier than you think. It's quite difficult to come up with a multivariate model that will spit out forecasts that are guaranteed to be coherent and yet is still flexible enough at all the levels to work. On top of that, we're often working in an operational context where we can't do that. We're getting these forecasts from different teams. Some may even be judgmentally adjusted, and therefore we have to work with those forecasts we are given and somehow make them coherent. So what this talk is going to be about is 2-stage processes. We're given some forecasts in the beginning, they don't respect our constraints, and we call those base forecasts. And then what we do in reconciliation is we make those forecasts coherent. We make them respect the linear constraints. Now, at this point, I should note that there is work on doing all of this in one step, or what they call end-to-end approaches for hierarchical time series. An example there, a paper similar in spirit to some of the work I'll talk about today, is by Rangapuram et al., but I won't say more about end-to-end processes today. Okay, so with that all in mind, what is forecast reconciliation? And here's a little bit of a history lesson. So typically, if you read the early literature on this, or if you were looking at this problem as I was when I came to Monash in the sort of early 2010s, mid-2010s, the idea would be that we would start with the vector of incoherent forecasts, y hat. Okay, so hats here are going to denote those base forecasts. Wherever you see a hat, it's that first step of forecasts. And they don't necessarily respect the aggregation constraints. Now recall we had that characterization earlier with S, and the way that reconciliation was originally explained and motivated was by regressing that y hat on the columns of S. We would use that S as a design matrix in our regression. And when you do that, you would then use the predictions that come out of that regression as our reconciled forecasts. And we denote those as y tilde. So typically in this literature, if you see tildes, it's reconciled forecasts. If you see hats, it's base forecasts. And then what does that look like? Well, one way that might look is that y tilde is equal to S transpose S inverse, S transpose Y hat. And then this method, because of its familiarity to us as something that comes out of least squares regression, was simply called OLS reconciliation. So that's where the name comes from. Now, I must say, when I first saw this, it made me very uncomfortable. Like a lot of people, I thought to myself, what are hats doing on the right-hand side? Why are we regressing on columns of this weird S matrix? So although the mathematics were clear, and although the results, when it came to forecasting accuracy, were very good, I felt something was lacking in this as a sort of way of explaining what we're doing with reconciliation. So that's what led to the geometric approach. But before we get there, one of the nice things about looking at this as OLS is that there's an obvious extension. If OLS works, let's think about GLS, generalized least squares. And of course, that takes the similar form, but where we now have a W matrix in there. And what should that W matrix be? Well, it's a GLS problem, so W inverse should be some sort of variance-covariance matrix. And it turns out in this setting that the covariance matrix of the base forecasting errors has some nice optimality properties. So y minus y hat, the base forecasting errors. We've got different ways of estimating that covariance matrix, which I won't go into, but this is sort of led to the state of the art, I would say, in forecast reconciliation, which is the MINT method of Wickramasuriya, Athanasopoulos and Heinemann, appeared in JASA in 2019. And if you've delved into this literature at all, you've come across this method before, okay? But as I said, I was always very uncomfortable with the regression point of view, and about the time I started working on this with Rob and George, I thought it would be better understood in terms of its underlying geometry. So what's the geometry of this problem? Well, the constraints, the aggregation constraints, or in fact, any constraints, these actually define a linear subspace, which I've denoted with the calligraphic S, which is some subset of the full dimensional space that we're looking at. I'll just note here that sometimes in the papers I use this math fractal notation instead. I'm now leaning towards the calligraphic one. It just looks a bit prettier. Now, one of the nice things about having this point of view is that it can be naturally extended to other settings. For example, if we have discrete data, then that coherent subspace S becomes a set of points. And that's something that we've actually explored alongside with reconciliation methods in a paper with Bohan Zhang and Yanfei Kang in 2023. It also naturally applies to nonlinear constraints, which we'll look at again later. But for now, let's keep it simple. Let's look at a simple 3-variable hierarchy, y total equals ya plus yb for real valued data. And we'll see a picture of that on the next slide. So imagine that this is a 3-dimensional plot. You've got your total on the vertical axis, ya and yb are on the horizontal axes. But because of our constraint, because y total must equal ya plus yb, our data is not going to be just anywhere in this 3-dimensional space. They will lie alongside the coherent subspace, shown there in grey. So all of those red dots are on the coherent subspace, okay? And fundamentally, the problem of forecast reconciliation is about having a forecast which is not on that grey area, and we need to find a way of getting our forecasts to move to that grey area. Okay. So then what is reconciliation? Well, reconciliation is just a mapping. It's just some function that takes us from the n-dimensional subspace to that coherent subspace where our data lives. And what are OLS and MINT? Well, they are actually just specific cases of psi, right? They're projections. They have nice properties, which we'll talk about in a bit, but that's just one way that we could get our forecasts onto that coherent subspace. So we can define projections in a few different ways, but something that's important here is the connection with optimization. So projections actually solve an optimization problem. And in this case, what they're doing is solving this problem here. So we're taking, I think the best way to understand this is that what we're trying to do is move to the closest point. So we start from our base forecasts and we're trying to move to the closest point on the coherent subspace. So we're trying to minimize, you could think of that as a norm or a weighted version of a norm, and we're trying to minimize that subject to our reconciled value being on the coherent subspace. Okay? Now, as I said, the reconciliation map can be more general than a projection, but projections do have these nice properties. For one, OLS always reduces our forecast error, and I'll explain what I mean by that in a bit. And two, MINT minimizes the forecast error in expectation. Now, again, when it comes to geometric interpretations, you want to kind of show this with pictures. So if I contributed one thing to this literature in the last 10 years, it's this picture. You know how people who do graffiti have their tag that they put when they do graffiti? This has been graffitied by me on whiteboards all across the world because every reconciliation problem I think of in these terms. So what do we have here? The arrow with the S on it is our coherent subspace. Obviously, it might be higher dimensional, but this is just a schematic. The 2 dimensions that you see there are where our forecasts live. So the blue dot, that's y hat, that's our base forecasts. The black dot, that's the value that we're trying to forecast. Obviously, we don't know what that is, but that's what we want to forecast. When we do reconciliation, we move from the blue dot to the red dot. We move to the closest spot on the coherent subspace. Okay? And what does that do? Well, it draws a right-angled triangle. Okay? It doesn't matter if we're in a really high-dimensional space. There's 3 points. 3 points is a triangle. And what every probably elementary school student knows, is that the longest line on a right-angled triangle is the hypotenuse. And here you can see that's the difference between y hat and y. Okay? So obviously the distance from y to y tilde is going to be less than that. And this is what I mean when I say that reconciliation always improves the forecast. No matter where I draw that black dot on the coherent subspace, the red dot will be closer to the black dot than the blue dot is. Okay, so with that in mind, why would we do mint? Okay, so with mint, it's a slightly different intuition. Now what we want to imagine is that we know something about the distribution of our base forecasting errors. And maybe what we know is reflected by those grey dots there. Think of that as a distribution around our target of our forecast, which is y. And of course, the shape of that little cloud is obviously going to depend on the variance and the covariances, okay, of that forecasting error. Now, we could do an orthogonal projection again, and this is all the possible values that you might get, and you can see that they're spread out quite widely on the coherent subspace there. But if we use the information in the covariance matrix, which is reflected in the shape of those grey dots, we just project along that R arrow, and we can see we get a much tighter set of red points around there. So it's in this sense that we understand that mint reduces the forecast error in expectation. It actually minimizes it in expectation. So it's optimal in a squared loss sense. Okay, so that's the fundamentals out of the way. Now, how did we extend this to probabilistic forecast reconciliation? And then I'll go into each of the 3 snippets. So again, part of what inspired this geometric view of things was that it was quite difficult to extend that regression interpretation to a probabilistic setting. And this is the ISF. We all know how important probabilistic forecasts are. I should note that there were some alternative approaches and still are some alternative approaches. So some ideas using copulars that were published in 2021 by Suhaib Ben Taeb and co-authors. And then also the team of Giorgio Corani have some ideas around conditioning on the coherent subspace, which are in some cases the same as what we've proposed and in other cases different. But the way that we looked at it, it sort of started in a paper written with Juyong John and Fotis Petropoulos, which, as a matter of fact, was initiated over coffee at the ISF in 2017. The idea was to reconcile draws from probabilistic distributions. And we later formalized that idea using the notion of push forwards, an idea from measure theory. So again, I just want to give the simple intuition of what we did in that paper. So again, this picture, my favorite picture. And what we have to think about here when we think about probabilities, what are we doing with probabilities? We are assigning probabilities to sets of points. Okay? So I want you to think about 2 sets. There is the set that you see between the dotted lines. That is shown in blue. Okay? That is a set in the full high-dimensional space. So when we have a base forecast, that's going to assign some probability to that blue set. But when we want coherent probabilistic forecasts, we don't want probabilities all over that blue set. Instead, we want probabilities in a region that lives exclusively on our coherent subspace, shown with the arrow with DS. And you can see that one example of such a set is that set A. Okay? Now, what's the connection between these 2 sets? Well, it turns out that every point in the blue set is mapped to a point in the red set when you use our reconciliation mapping psi. And what we're showing here is a projection, just like what we showed before. Okay? So that's the connection between these 2 sets. And the idea of a push forward, or the idea of how we've framed forecast reconciliation, is that we simply assign the same probability to the red set as is assigned to the blue set under the base forecast. Okay, so that's the intuition. Now a little more on the maths. So mu hat is a measure on Rn. A is a region entirely within our coherent subspace. Psi is one of our mappings again. Psi inverse of A is what's called the pre-image of A. What does that mean? Well, every point in the pre-image is mapped to A by the function psi. And then our reconciled measure mu hat is just obtained by assigning the same probability to those two sets. Okay? So that's what's called the push forward. As I read more on measure theory, I realize some notational conventions. So one that I'm starting to use a bit more is this psi hash mu hat that you see at the end as a shorthand for all of that. Okay. But now let's go back to optimality again. Because all we've done so far is just to find how we get a reconciled distribution from some incoherent base distribution. So what is the optimal psi? In the point forecasting world, we knew that MINT had some optimality, at least for squared loss. So we knew projections worked there. But before we think about this in the probabilistic setting, we have to ask ourselves, what does optimality even mean when we're talking about distributional forecasts? And again, one way that we think about that, common in this community, is through scoring rules. So scoring rules take a distributional forecast more specifically, and they take an observation and they assign some score that measures the quality of the forecast. So in the context of probabilistic forecasting, Wickramasuriya has a paper showing that the log score, MINT is still optimal for the log score, at least when the base forecasts are Gaussian, at least in the Gaussian case. But what about everything else? And for other cases, what we propose doing in a 2023 paper with Pawasala Gamakumara, Rob Hindman and George Athanasopoulos was to optimize the scores using a data-driven approach. So what's the guts of this approach? We obtain a sequence of base forecasts and corresponding realizations. We parameterize this mapping psi with some vector theta, so psi of theta as you see there. For example, what we use in the paper is a linear combination. That's not necessarily a projection, although it nests projections. There's a sort of shift term D and this matrix G. And then we optimize the following. We just minimize our scoring rule. Where in the left-hand side, what's going in is that push-forward measure, and on the right-hand side is YT. Okay, so a few practicalities here. We've used log score, energy score, and variogram score. You can use other scores as well. How do we get this sequence of observations and forecasts? Well, typically we'll use a rolling or an expanding window scheme. I've abstracted away a bit the issue of the forecast horizon, but you can use different values of theta for different forecast horizons. And quite an important one is that when it comes to working with this push forward, we often draw a sample from the base forecast, reconcile each of the points, rather than working with the distribution itself. And because of that process of actually drawing samples from the distribution and plugging them into the scoring rules, that introduces an approximation. So when we do this optimization, we're typically using stochastic gradient descent rather than something like gradient descent. So that's the practicalities of how you do this. Now, I don't have time to talk about the empirical work we've done in this paper, but just some main takeaways, and that is that if our models are heavily misspecified, so for example, if we assumed independent and Gaussian-based forecasts, we found that score optimization outperformed benchmarks, including those that are based on projections. On the other hand, if the models were less misspecified, for example, we did some sort of joint bootstrapping on the base forecasts, then we found that projections were working fairly well, quite similarly to score optimization. So the way I like to think of this type of score optimization approach is that it gives the forecaster a second chance. If you have very bad base forecasting models, you're able to correct for those through score optimization. If, on the other hand, your base forecasting models are quite good, then doing reconciliation using the probabilistic version of MINT is going to be a very good, robust choice. The other nice idea about this is that it allows you to target your reconciliation mapping towards some end goal that matters. And in this case, it was probabilistic scoring rules. But something that bugged me a bit about this paper is that no business is having their profit and loss impacted by the probabilistic scoring rule. So instead, we started to think about what are some other loss functions, ones that arise in actual business problems, that we can adapt this methodology for and use it for. So that leads us to the first of the 3 snippets that I promised on quantile optimal reconciliation, and the kind of gist of it is in the name. It's joint work with a postdoc, Hossein Alipour, George Athanasopoulos again, and my now former colleague at the University of Sydney, Nam Ho Nguyen. So many forecasting problems, including, for example, the standard news vendor problem that people learn in a first-year ops management course, involves the pinball loss function. So this is the pinball loss function here, where the I notation is used to indicate 1 or 0. And to statisticians, we know this function because we know that quantiles, or one definition of quantiles, is that it minimizes the expected pinball loss. So this is what we want to now bring into the world of forecast reconciliation. So what do? Well, now we are targeting quantiles. So what we want to optimize is a function that looks like this. Notice that we've got a sum over n. So this is aggregating the quantiles for each node in our hierarchy, for each time series that we're looking at, or aggregating the pinball loss rather, I should say. We still sum over a training sample, but then what goes into the loss function are y's, our outcomes, and q tildes. Our q tildes are the quantiles of our reconciled forecast. Now, how do we ensure that those q tildes are indeed the quantiles of our reconciled forecast? Well, we're going to add some constraints in, and we're going to add in precisely the constraint that I alluded to on the previous slide. So remember, our quantiles are solved by an optimization problem themselves, which is to minimize the expected value of the pinball loss. Okay? So here the expectation is taken with respect to the margins of y, of the reconciled distribution. You may be saying, where does the theta come in? Where does our reconciliation parameters come in? Well, the yi tildes, this reconciled distribution, is going to depend on those reconciliation parameters. Okay, so this is what in the optimization literature they call bi-level optimization, because the same function appears in the constraints and in the objective function. It's further complicated by the fact that pinball loss is not smooth, and it's complicated again by this need to approximate the expectations in the second level with sample equivalence. So how did we get around this? Well, 2 layers of optimization. The first one is to use a smooth version of pinball loss. So this function approximates pinball loss and converges to pinball loss, in fact, as beta goes to infinity. So by using this smooth version, we're back in the game and we're able to use things like stochastic gradient descent. So here's what that smooth function looks like. As I increase beta, eventually we get to a point where you can't distinguish it with the naked eye. So just winding back, remember, this is the problem we want to solve, and we're looping in 2 levels of approximation. In orange, you can see the betas. We're replacing the pinball loss with the smooth pinball loss. And on the bottom, we're replacing the expectation with a sum where we now draw these y tildes from the reconciled distribution. Okay, so I have presented this before. This paper's been quite a while in coming together. But one of the reasons for the delay is because we've got some new theoretical results. So to those who have seen me present this, this is the new bit. So let's say that f theta is the problem we want to solve. And f beta of theta is the approximation induced by using the smooth pinball loss. Fj uses the approximation from the pinball loss, the smooth pinball loss, and using the sampling. What we've proven now is that the minimizer of the approximate problem converges to the minimizer of the true problem, and that involves proving these 2 limits. Now, I won't go into, it's the last keynote. This is probably too technical a talk already, so I won't go into the details of how we prove that, but they will be available in a working paper very shortly. One last little thing that I'll put in The optimization is done by stochastic gradient descent. There's a few tricks about passing the gradient through the argmin in the lower level. One thing we realized here is this is actually a biased gradient estimate. So we had to go back and check the literature, and the variant of stochastic gradient descent we use still converges if these two conditions are met, and those are proven for the functions we consider. The main takeaway argument here is that stochastic gradient descent sometimes feels like a hammer, and when you hold a hammer, you hit nails, you think all your problems are nails, and yet it's important, and you learn this when you work with optimization people, it's important to check that your nail is indeed a nail before you decide to hit it with the hammer. So check for your convergence of SGD. Okay, just quickly, I'll go through an empirical study. It's the Australian tourism data set. We look at a subset of series, in fact, it's a grouped hierarchy. Seasonal ARIMA is used for the base forecasts with different distributional assumptions. We train on 10 years of data, and here is a table quickly summarizing the results. In each column, you see different quantile levels. The quantiles, the pinball loss, the aggregate pinball loss is what you see in the table. We've got base forecasts, forecasts based on OLS reconciliation, WLS, MINT, and our quantile optimizing approaches at the bottom. The stars here refer to what is in a model confidence set, so it's a way of testing significance. We can see that for this particular example, for the bottom, the lower quantiles, they're not significantly different. All of these are in the same model confidence set. But when we look at the upper quantiles, particularly the highest quantile, not only do we improve on the base forecasts, significantly so in fact, but we also improve on OLS, WLS, and MINT. So here's some motivation for actually using these optimization type approaches. Might not work for all quantiles in every data set, but here we have found one where it does. Okay, so that's what I'll say about the quantile optimization, and I'll now move on to some new work on nonlinear reconciliation. This is joint work with Han Li from the University of Melbourne, as well as Daniele Girolimetto and Tommaso Di Fonzo, both from the University of Padova. So the question is, what if the constraints are nonlinear? And the way I sort of became aware of this problem is Han Li is working a lot in mortality data, and in that particular field, the mortality rate is a ratio. It's a ratio of that you're trying to forecast. So mortality rates are deaths divided by exposure, but there's also a lot of economists in here, and we know that unemployment rates are the number of unemployed divided by the labour force. Now, a legitimate question, if you're just dealing with ratios, is just log linearize and then everything becomes linear again. However, in both of these examples, you may also have some aggregation going on. So, it might be the case that you have a geographical hierarchy for your deaths and for your exposure, and there are linear constraints in play there. So if you log linearize everything, you're going to make those linear constraints non-linear. So we need a non-linear approach. Okay, so to formulate the problem, we formulate it in terms of constraints. So G1 to GC are our C constraints, or compactly just G of Y. The level set of points whereby gy equals 0 is our coherent surface, or you could think of it as a coherent manifold. I'll continue to use S to denote it. And nonlinear reconciliation solves the following problem. We've seen that optimization problem before. In fact, it's exactly the same optimization problem. The only difference is that this constraint at the bottom, that Y belongs to the coherent subspace, in fact, is nonlinear now. Okay? But you can still solve that using Lagrangians and the like. Okay, so at the moment our focus is still on point forecasts and on projections, but we've made a few advances theoretically. In the first case, we just look at convex constraints, and there what we're able to prove is that reconciliation is guaranteed to improve upon base forecasts, but only in what is called the hippograph, and we'll see that in a picture shortly. For more general constraints, we take a different approach. And what we do is that we throw another optimization problem out there, which is to find the closest point. So we're finding a critical point, and this is the closest point that is on the coherent manifold, but that is equidistant from the base and the reconciled forecast. And what we're able to show is that this defines a ball, in which reconciliation always outperforms base forecasts. We then have an expression for the radius of the ball from which we're able to make some hopefully important practical conclusions. Okay, so here's the example of a convex function. And when I talk about the hypergraph, I'm talking about the shaded grey region underneath that black line. So the black line is our coherent surface, the grey area is beneath that. Again, 3 points. In pink now, y hat is our base forecast. In black is our true value that we're trying to target. And is blue, the y tilde, that's our reconciled forecast. So we're still doing projections. They look a little bit different. They're now orthogonal to a hyperplane that is tangential at y tilde. But you can see here, you're still able to prove that at least as long as the pink line is in the grey region, it's going to be longer than the blue line, because the angle made at that blue point is greater than 90 degrees. Okay, so that's an intuition. It works in higher dimensions. You might think this is only 2 dimensions, but remember, a triangle is a triangle. It has 3 points, no matter how many dimensions you look at. That's what we were able to prove about the convex function. In the more general case, as I said, we look at this approach where we find a critical point. It's now shown as y star. And that y star basically is at the point where the hyperplane between y hat and y tilde intersects with the coherent subspace. The ball that I was talking about is the grey ball that you see behind there. So what do we know about this ball? Well, we know the radius of this ball. Okay? And that is a hideous formula, again, to throw up at a very late stage of the conference. But just to give you an idea of what's in here, and then I'll discuss the intuition on the next slide, what we see in here are Lagrange multipliers from the different optimization problems we look at, and the capital J matrices are the gradient vectors of our constraints, the gradient vectors of our constraints. So let's skip forward to the discussion of how this is useful. How can we actually use this theory? Well, it actually gives us some guidance about when nonlinear forecast reconciliation is more likely to succeed. And when is that? It's when our base forecast is far away from the coherent manifold, because that particular distance is related to the Lagrange multipliers. Okay? So if you're far away from coherence, you're more likely to do better from reconciliation. An interesting one is that all of those tangent vectors, those gradient vectors, they are related to the curvature of our nonlinear function. So if our constraint function has lower curvature, you're going to do better when you do nonlinear forecast reconciliation. Now, this makes sense, because in the limiting case, if there's no curvature, if it's just a flat line, we know that reconciliation always does better. Okay? What we have here is a result that tells us that as it gets more and more wiggly, as your constraints it gets more and more wiggly, it's a little bit more risky to do reconciliation. You might actually make the forecast worse. Of course, it will work better when the reconciled forecast is in a high probability region of the true DGP. For example, if, going back to the picture, if our true value is far away outside of that ball, reconciliation may not work. And then finally, if you have some convex constraints and if the base forecast is more likely in the hypergraph of those convex constraints, then you're going to do better. This is a visualization of some simulations that basically show that intuition. So what you have here is on the vertical axis, this is the percentage of times that reconciliation doesn't work. The base forecast is actually better than the reconciled forecast. The numbers are quite low. These are percentages, so it's less than 10%. Along the horizontal axis, we're looking at the curvature of our test function, and the color refers to whether you're in the hypergraph or whether you're in above the curve, and how far above the curve you are. So what we see here is that in the blue dots are all sitting along the bottom because they're in the hypergraph. We're always doing better there. But if we move into the epigraph above the curve and we move to those green lines, we see that those green lines get worse as the curvature of the function gets worse. Okay, so we have some understanding now of when this projection type nonlinear reconciliation works. We also have a application on exposure, on deaths, and on mortality rates. We have the data for the US as a whole, as well as 9 census regions. As we said before, E and D are going to respect aggregation constraints, linear constraints, but M, the mortality rate, may not respect those constraints. However, M is going to equal D on E, so that's where the nonlinearity comes in. Okay, and what we see here is just a summary of results. On the left, you see when we only look at the rates. On the right, we see the others, so the deaths and the exposures. A summary of all forecasts is on the right-hand side. And the way that you read these plots is that if you're on the left, it's doing better. If you're in the blue shaded region, then you're in the same sort of region of significance. But if you're a red dot, then the best method is doing significantly better than all of the red dots. So what we see here is we're doing significantly better than the base forecasts. OLS is not doing so well, but when we do the sort of MINT type approach, we do significantly better than the base forecasts, as well as another benchmark mortality model. Okay, so that's so much for the nonlinear forecasts. I'll now talk about beyond hierarchies. So if you've been patient, if you don't work in hierarchical forecasting and you've been patient enough to sit through to now, I can finally tell you how you can use this in general. So let's say we're still interested in multivariate forecasting, but we don't have linear or even nonlinear constraints. So my question is there anything interesting about forecast reconciliation? And surprisingly, there is. We don't need to have hierarchical data to use forecast reconciliation. So I'll discuss now some new work on forecast linear augmented projection, or what we're calling FLAP. By the way, this is joint work with George, Rob, the usual suspects, as well as a PhD student, Fin Yang. So our target is now to forecast some Y, and there are no linear constraints here. Okay? But what we're going to do is construct some new synthetic series. So we're going to construct C as linear combinations of the Y's. Now the choice of phi here is arbitrary. It doesn't matter what you choose. There are some things that are better to choose than others, but for the theory to work, phi can be anything, as long as you know what it is, and you know what it is because you choose it. What we now do is that we've now got an augmented vector. We've got a vector that has both Y, our series that we care about, as well as these new components that we don't actually care about, but we've still got them. Okay? And this augmented vector follows some linear constraints. So what are we going to do? We're going to forecast all of the components. We're going to forecast that full vector. We're going to forecast Y, which we care about, but we're also going to forecast C, which we don't actually care about. And then we're going to reconcile it using MINT and get a new set of forecasts. Now, we know from the properties of MINT that we're going to reduce forecast variance for that vector as a whole. The key idea that makes this thing work now more generally is that we've proven the same is true when only looking at a subset of the hierarchy. And there's some conditions for that to be true, but in our case, the Y satisfies those conditions. Okay? Obviously, you need to preclude certain edge cases in phi and things like that. Okay, so what does that mean? We can now reap the benefits of reconciliation even in problems where there are no constraints at all. Okay? In a similar vein, we prove that the forecast variance is actually non-increasing as we add more and more and more of these synthetic components. Okay, so you might be thinking this is too good to be true, and it is. Originally, FLAP was going to stand for free lunch augmented projection, but as we know, there is no free lunch, and we didn't want to be so provocative in naming this algorithm. So where's the catch? The catch is that all of our proofs assume that the error covariance used in MINT is actually known. But in practice, of course, this matrix is estimated. And if you just keep going and arbitrarily adding more and more and more synthetic components, eventually the quality of that estimation is going to deteriorate with higher dimension. You can use all the shrinkage tricks that you know, but something's going to go wrong. However, what we've seen in empirical work is that for finite dimension, the benefit of FLAP can outweigh the errors in estimating the covariance matrix. Okay. Now, this, like I said, all of these things in a way were motivated by geometry, So here's the geometric intuition of why flap works. We start off with our horizontal axis here. This is what we care about. We've got a true value y in black and a base forecast y hat in blue. We now augment our problem. We synthetically create new dimensions. Okay, so now we've got these components that are on the vertical axis here, and we get a new forecast given in blue over there, and we also get a new true value given in black over there. Because we've constructed these things as linear combinations, there's a coherent subspace shown in black, and if we project to that coherent subspace, we throw away the information about the components, we go back to y tilde, and y tilde is closer to the black dot than the blue dot. Okay? Now again, this is mainly intuition. I could have drawn this in a way such that it doesn't work, but if you want to fully understand it, you can deal with the tedious linear algebra that's in the working paper. Okay, so a quick application, and then I'll wrap up. It's based on the Fred data. All the macroeconomists in the room are familiar with that. And what we actually looked at here are different horizons. In blue, you see the forecast from a dynamic factor model. In orange, you see where the base forecasts are from an ARIMA model. The dotted lines indicate where we start from, the base forecasts. And then along the x-axis, you see P, what happens as we add more components. And what you see in this example is that we typically do better. We keep doing better up until the black line, where we have as many components as underlying series. But then from there on, things start to deteriorate because we have problems estimating the variance-covariance matrix. But again, take any method you like, you can improve your forecasts simply by adding this on top. Okay, so this doesn't replace any of your favorite models, it's just something to add on top of your favorite models. Okay, I said they were in various stages of incompleteness. This one is the most complete because we have a working paper and we also have an R package that is actually available. So take a photo of that slide if you want to use the flap method. Okay, I know I'm getting to time, so I'll wrap up with just a few concluding statements. And what I feel I want to do here is sort of say something for the young researchers out there. When we first came to this problem and we started thinking about it geometrically, we were a bit unsure of ourselves to start off with because we thought we're really just proving existing results in a different way. And how are referees going to take that? Are they going to think it's worthwhile? But had we not done that, we wouldn't have made the advances that we made in, well, all of the advances you saw today, in probabilistic forecasts, nonlinear forecast reconciliation, even to some extent in flap. So sometimes you have to take a step sidewards before you can take a step forwards. So don't be afraid to do that. I know people are rushing to get papers out, but sometimes you need to take a sideward step. The other thing, in a way, this talk, I think, and this area has touched a lot on theory, methodology, and application. And one of the things I like about this community is that you meet other scholars who work in all of those areas. So again, to the young researchers, don't pigeonhole yourselves that I only do theory, or I only do methodology, or I only do application. Try and branch out and work on the other areas too. And of course, we all have our strengths. So although we shouldn't neglect any of these, it helps if you can work with the right people. And that is a good point for me to say who the right people are in my case. So these are my collaborators on the papers that I spoke about today in detail. There are a few other photos that I would have loved to have had here, but I did only have 1 hour to talk. And then I'll finally wrap up with some comments on forecast reconciliation. I think it's a very practical and interesting problem with many open questions. So some things that we're looking at in the future is how we can guarantee the calibration of probabilistic forecasts. We're looking at various multi-objective optimization angles on reconciliation. And of course, there's always the desire to look at different loss functions. So my last bullet point is to jump on the bandwagon. This is a fun area to work in. And with respect to that, I'm being very brazen now and finishing off with 2 links. The one on the left is a link to a postdoc opportunity. We are hiring a postdoc to work on forecast reconciliation. So hopefully that works. And I'm very happy to see people taking the screenshots. The one on the right is a link to these slides. I published these on GitHub. As the other papers are completed, I'll put references to working papers up there. So that'll be a live link. But that's it. Thank you again. And let's get to the closing ceremony.
Thank you, Taz. I always learn something new when I listen to Taz, even when he's talking about a paper that I'm a co-author on, especially when I'm about other papers. I did not know the word hippogriff. I knew about hippogriffs, which are mythical beasts, not hippogriffs. Okay, any questions? Yeah.
So Taz, it's great talk. So my question is about your no freelance statement. Do you have any guidance to about this convex matrix estimation? Because under your theory, you assume all of them are known, but in reality, we don't know it. Any of your computational experience you can share with us?
Yeah. So in terms of theory, it's proved quite tricky. When we initially worked on it, we thought, can we look at some asymptotics as the p goes to infinity and as t goes to infinity? It was quite tricky to work with theoretically. So that's an opportunity for someone who wants to look at the question again in that way. What we know empirically, though, and we've seen, what I showed you there was not even the strongest example empirically. We know empirically this works sometimes up to a very large number of components, even when the components are randomly chosen. The phi matrix is just randomly generated and it works. So again, theoretically, I think there's more to learn there. I don't have an answer for you in terms of rates of convergence, but it would be something interesting. But in practice, it doesn't really matter that we don't know this matrix, as long as we can get a good estimate of the matrix. And typically we can do that in many empirical settings.
Thanks for the great talk.
Thank you.
Does it help to sample different psi matrices and optimize the expected loss over these different sampled psi matrices? Because then you would, maybe favor different subsets of correlations between your different series?
That's a very good question. I haven't thought about that specifically, but we have looked at things sort of tangential to that. So what we know is that you can take weighted combination. If you reconcile something, you could take a combination of something that is reconciled. Okay. So in other settings, we've looked at combinations of different sets of reconciled forecasts. I should also flag the work that Daniele presented at this conference, where they look at the interplay, Daniele Girolimetto, the interplay between model averaging and forecast reconciliation. So I only became aware of that about 24 hours ago, so, but it's something to look out for that maybe looks at what you've asked there.
Yeah, I'm new to the area of hierarchical forecasting, but I was intrigued by your pinball loss optimization. So the quantile there you assume to be fixed across the hierarchy or changing across the hierarchy?
Sorry, the quantile is what?
You had the pinball optimizing on the pinball loss. So
Yes.
Then you need to have a quantile in there, like a target.
Yes.
Is that the same across the hierarchy, or is it changing across the hierarchy, or does it matter?
Okay, so what we've done is we've assumed, so the level of pinball loss, the alpha level, is the same across the hierarchy. Although there's nothing in what we've done that precludes you from having a different alpha at different levels. But I think the more interesting problem is how you put them all together into a single loss function. And at this stage, we just aggregate. Now, you could take weighted combinations, you could take different things. So I think that's a very interesting open question. But with respect to what you're saying, that the quantile level, and I think I know where you're going, this is like a supply, a safety stock, sorry, they can be different and the methodology will work. We haven't looked at that empirically, but there's nothing stopping you from doing that.
Thanks for the talk. It was really useful for me since I'm working with nonlinear cases. I wanted to know that, for example, for the convex case that you were talking about, the minimization problem, do you have any closed form for the minimization problem? Or if you don't, then what kind of an approximation approach are you taking?
Okay, so for the optimization problem, whether you have a closed form or not, will typically depend on the nature of the constraints themselves.
Yes.
As I think you know, because you've also done some work in this area. So the optimization is still done numerically, because in general it's going to be done numerically. I mean, except for maybe in the linear case, obviously you get a closed form expression. In non-linear cases, it will be rare to do so, so anyone writing software for this kind of thing is going to do that numerically. Yeah. Thanks. Yeah.
Since you raised the question of software, when are we likely to see an R package or a Python package that implements some of the FLAP one you mentioned, but the quantile one and the nonlinear one, are they underway?
Okay. So the nonlinear one is underway. There's a GitHub, but we're keeping it private until the paper comes out, which should come out soon. So that's being authored by Daniele. I think I'm the only other person on the GitHub repository, but I haven't touched it. So that will come out when the paper comes out. So hopefully in a few weeks, actually, we're really close with that one. For the quantile stuff, that might take a bit longer to get the package out. You know we want to do it, but that needs to be tidied up a bit more. So that might take a bit longer. Yeah.
Let's leave it there. Thank you, Taz, for a wonderful talk and a lot of fascinating insights. Please join me in thanking Taz. We now have a 10-minute break, so be back in 10 minutes for the closing ceremony.